Bismillah ar-Rahman ar-Rahim. Volume and flow measurement. First of all, gas volume measurement. We have, first of all, the Benedict Cross spirometer, which you can see that has a bell and some water in a pot. And we have a pen recording on a chymogram. And of course, we have two pulleys to make the string go through it. And then after that, we have the vitellograph. You can see as if it is a concertina. Its pivot upwards is pivoted, and there is a scripper. Whenever the patient expires, it activates the system, and a scripper writes on a chart. These two methods give a very low reading of low volumes. Now we have the domestic flow meter, which is made of two compartments and a rod CC with a lever. We can use it during expiration or inspiration, and as you can see, the direction of the flow with the concertina and the reading of the data. After that, we have the right spirometer. Of course, right spirometer is being used in anesthesia on the expiratory limb, where we have a van and then we have slits all over to make the air circle, and then this van is attached to a gear system and a pointer and a scale. So whenever the patient expires, it moves the system and it records the tidal volume or minute volume. The problem that it's inaccurate because it's difficult to be calibrated. And after that, we have the electronic meter, which is based on non-moving parts. We have a van. The van is being beared on a jeweled bearing, as you can see. And then we have two pedals with 6 arms. And whenever the patient expires, these vans move and activate the diodes, the light, and then the movements of the light through these movements of the van records the volume. After that, we have liquid volume measurement. We have the dilution method. We inject the amount of labeled RBCs to know the amount of RBCs volume. And then we deduce the radioactivity by a counter. And then we record, first of all, the end result. We record the volume from the concentration of the dose of the labeled RBCs, and the red cell volume can be calculated. Of course, we measure also the plasma volume by radioactive albumin, and we can at the end result we can measure the blood volume by the plasma volume in the numerator, and the denominator contains 1 minus hematocrit. You can figure it out. It's the right figure. After that, we have the most important is the gas flow measurement. We have the rotameter, as you can see. It's made of 2 glass tubes, and they are inclined. You see, the downwards is much less than the upwards. And then we have what we call a bobbin, and then whenever the bobbin goes up, the annular space around it is increased, making the resistance less. It'll come a point where it will be settled. The force acting upwards equals the force of the gravity, and this is why it is called constant pressure variable orifice flow meter. Of course, the problem of sticking, if it is upward in a maximum situation on the lower part of the flow meter, and of course this movement of the bobbin by the slits present makes static electricity. All this can make the bobbin stick. Instead of that, we use to avoid this problem a ball, but the problem of the ball that we cannot denote really the site of the measurement, whether it's upper one or we take from the middle. Method to decrease the static electricity: either I coat the tubing system, or I make some sort of a wiring system to dismiss this static electricity. The accuracy of this flow meters, of course, it depends upon the type of the gas being used, of course, because each gas has spatial density and so forth. And the accuracy is around 2.5%. Of course, we can use different flow meters for low flow and high flow. The needle valve, as you can see, is attached to the flow meter. The speed almost is the speed of voice. We have the gland and the gland knot, which decrease the leak of the air, and then you have a bacterial filter. It induces the pressure, which can act the pressure of the ventilator. The position of the individual flow meters, of course, is important. Whenever we have a carbon dioxide, the mineral is broken, and suppose oxygen is in the beginning, it will leak. So, to solve this problem, the oxygen is being put in the third one, as you can see, and the nitrogen oxide, the first one, or making a special route for it. Now we have what we call of course, we have also the pneumatic mix involved with the method to cut off nitrogen oxide whenever we have an oxygen failure. After that, we have the right peak flow meter, as we see. It's similar to the right spirometer, but it measures the peak flow rate, which is normally from 400 to 500 liters per minute. Whenever it reaches 100, less than 100, that makes the physician suspect of respiratory problems. It's made also of a van. This van is attached to a spring, and then whenever the patient expires, this van is being turned, opening, increasing the opening so that the expiratory air can be released. This is why we call it also variable orifice, constant pressure, because the pressure of the spring adjust the movements of the van, and then whenever the measurement is finished, there is a needle or there is a button to return the system to the 0 point. A pneumotachograph, as we can see, is made of 2 compartments separated by a large mesh to assure a laminar flow, and it's heated so to prevent the condensation of water. This drop of pressure is interpreted by a microprocessor to flow, as you can see. And then we have what we call the pitot tubes. Pitot tubes is made of two of differential pressure transducer, as we can see, and 2 tubes in the course of the flow. You suppose this is a respiratory way, and we have 2 tubes. Of course, definitely the tube facing the flow will yield much more pressure than that away from it. Now we know that the fluid has 2 types of energy. We have the potential energy, which is responsible for the pressure, and the kinetic pressure, which is proportion to the square root of the velocity. So in another word, we find that the kinetic energy, the moving, is going to be proportional to the square root of the velocity. The point is this diameter of the breathing system varies, so we must adjust it so that it can there is a proportional relationship between the flow of the gas in this breathing system and the velocity of the pitot tube. Of course, we shift this velocity to flow by a special adapter. After that, we have the mass flow meter. Is made of, as you can see, a compartment, and there is 2 thermistors. This is the thermistors are being heated by electrically. In case the flow is very high, it will take much temperature, so it will affect the results. So we must have a method to increase its temperature. Of course, the other one, the first one, measures the temperature of the fluid flow for the first beginning, as taking it as a reference. And then we have, of course, the measuring mass flow meter. Now we come to the liquid flow measurement. We can easily multiply the drops by the volume, by the rate rate of the drops. Of course, each drop has a special density and accordingly. And then we must put in our mind that the drop is being held by its surface tension, and whenever the drop is being increased, its weight will increase, will overcome the surface tension, and the force of the gravity will detach it and will be dripped accordingly. And we have after that the drip counter. The drip counter simply is a part where we fill only a third of it with the liquid, and then we have a light source, and then we have a receipt of this light. Of course, this light has been interrupted by the drops, and this is why this is how we measure the drops. Of course, after that, this is called gravitational, but it depends upon the gravity, and the gravity has, of course, problems. After that, we have the infusion pump. As we know, it is a volumetric pump, and we can. It depends upon the disposable cassette, and we have the infusion pump, which can infuse around 1,000 millimeter per hour. And this syringe pump or infusion pump can be adjusted by electromechanical encoded cards in the front of the apparatus to adjust according to the drug given. Now we have the last one, which is the target controlled infusion. This target depends upon it is a microprocessor, depends upon the three compartment pharmacokinetic model, and it can adjust the dose of the drug given by feedback mechanism to adjust the concentration in the blood according to the stress, of course, of the patient. Of course, we have another variable orifice flow meter for liquids. As we can see, we have the dye dilution, and we have the isotopes dilution and thermal dilution, ultrasonic measurement, and electromagnetic flow meter, and the Fick principle. The Fick principle, as we can see from the first the medical rods, we use either the oxygen consumption or the CO2 production whenever the patient inspired oxygen with a non-rebreathing valve. We can estimate the amount of oxygen consumed in a minute. Suppose it's 250, and we have an arterial blood sample and giving an amount of 150 milliliter per liter, and we take a sample from the mixed venous blood. Suppose it's around 200. I'm sorry, we are talking now about the Fick principle, which we depend upon either oxygen consumption or CO2 production. So suppose that we found that the oxygen consumption is around 250 milliliter per minute, and then we get an arterial sample. We find it's around 200 milliliter, and a venous sample which we find it 150 milliliter, and by subtracting the 200, we'll find that the oxygen consumption is around 550 milliliter. This is being induced by a flow of 250 milliliter per minute. So whenever I divide both of them, I can yield the cardiac output. So we are utilizing oxygen consumption in 1 minute to measure the cardiac output. The second method is non-invasive cardiac output measurement by using of the differential Fick principle to measure elimination of carbon dioxide through a system. As you can see, it's a rebreathing system, and we have two sensors. One of them is the flow sensor, and the other one is the CO2 concentration sensor. So we can know, if we know the total flow, the amount of carbon dioxide present or the flow of carbon dioxide present in this total flow. You see, so and this is a non-rebreathing valve. This non-rebreathing valve is being used every 3 minutes to call it, so that the patient will rebreathe every 3 minutes, and a calculation will be done. Simply we have the figure of the cardiac output. Normally it's the flow of carbon dioxide minus the carbon dioxide concentration in the arterial minus, or in the venous minus the arterial. This is the normal cardiac output which we can estimate from the normal effect principle. In this system we have the opportunity that if we rebreathe for 30 seconds, no much change will occur in the mixed venous blood of the carbon dioxide. This is the method to create two cardiac output equations. So whenever these two cardiac output are joined together, whether the patient is normally non-breathing or rebreathing after closing this valve, we can create the cardiac output figure by noting the flow of the rebreathing minus the flow of carbon dioxide of normal non-rebreathing over the arterial carbon dioxide non-breathing normal minus arterial carbon dioxide rebreathing. So this is the difference. We are minimizing the list from the bigger one. You see, so this is the point, that the valve is being closed every 3 minutes, and we utilize the estimation that for 30 seconds of mixed venous blood, no much change occurs. This is how we utilize the point to measure the cardiac output non-invasively, because we are not doing an arterial sample or taking a mixed venous sample, but we are utilizing the end-tidal CO2 as a measure of the arterial CO2, and we must put in our mind that the shunt equation must be used in this equation. It's around 5%, and it can be estimated through knowing the concentration of oxygen used and the saturation. So the correlation between both of them can yield how much is this shunt equation. I hope I summarized this subject in less than 15 minutes. Thank you very much. Wassalamu alaikum wa rahmatullah wa barakatuh.